In the next subsection, I want to show you some primitives that will be part of bigger parallel algorithms, in particular for parallel sorting. But we should also show that you have to learn some new building blocks for these kinds of parallel algorithms. We'll see that most problems are not embarrassingly parallel, but they contain some parts that are almost embarrassingly parallel. So many problems have this double nature. There's parts that are easy to parallelize, but then there's other bits where they seem to build on previous results all the time, and so you need tricks to get these steps done efficiently and still make use of the parallelizable part. I know that's so vague that it's close to useless. Maybe it'll make sense after you've seen the examples. It turns out that luckily, in a way, there are some building blocks that are useful many times, and we'll study some of those. The first of these building blocks is called the prefix sum problem. And it's formulated in an abstract way so that it is useful and applicable to different scenarios. It may look a little unmotivated at this point, but bear with me, you'll see on Monday what it's good for. The input is an array of numbers, as so many times in this module. The goal is to modify this array, so you're allowed to do this in place, to modify the array so that afterwards it contains the prefix sums, which means at position I, you're supposed to have the sum of the elements up to and including position I, which are I+1 numbers, I guess. So here's an example. Here's the input. Here's the output. Note that so we always have that the first two entries are the same. If there's zeros, that means some things stay constant in the other array. And an entry up to here, so it just sums up all the numbers up there, and that matches. It sums up to 15. I guess the definition of the problem is easy enough. Now again, bear with me for why this is a useful problem. Without telling you much, let's have a vote on what you think is possible for this. And now first, just sequential, right? So you, I'll maybe show the problem again. You're supposed to do this just sequentially, standard algorithm, coded in Python, whatever you want. How fast can you do it? In a way, there's no wrong answer to this question. Well, maybe there are some wrong answers if it's impossible. But if you vote something, if you vote the highest number n cubed, it's never wrong, right? Because you can do it in that as an upper bound. But maybe that's not the most interesting algorithm then. What did I say? Wait till 40. 34. Do we get some more? 35. I should have split this up and now first show you the code and then have you vote again. In the interest of time, let's not do this though. The answers are very mixed. A few went for the safe option of n cubed. I guarantee you it's doable in n cubed time. A big O of n cubed is a safe bet anyways. Yeah, if you can do it in log n time, please find me for the thesis later. Sequential time, right? No, sorry, I'm not supposed to mock you much for this. So linear time is what we can do. Sequentially, I think this is inevitable because you need to read the array to produce the result. If you think about just the last entry, how are you supposed to do the sum of the entire array? Well, the last entry is the sum of all the numbers. How are you supposed to get that sum without inspecting every position in the array? I think this is not possible in the worst case. How can you do it in linear time, though? Here's the code. It's very nice and slick and simple. Oh, you don't see it. I forgot to switch back. There we go. So I was waving around on this slide. The last entry in the array is the sum of all numbers, and you need linear time to find that. And here's the code. For the dramatic effect, it's just 2 lines, really. The trick is you compute the sums from left to right, and then you use that. The next sum is always the previous sum plus 1 more element. That's how you can compute all those sums. Even though if you wanted to do those, we'll come to that if you do it in parallel. If you wanted to jump right in the middle and compute one of the sums taken out in isolation, you always need linear time in distance to the beginning. But if you do it sequentially, you can build on the previous result. That's great. It's actually very, very cheap. You do the number of additions that would be needed for just computing the last entry in the array, the total sum. But along the way, you get for free all the other partial sums. It's just convenient that you can leave them in the array. Now, the big problem for parallelizing this, of course, is that's maximal data dependency. Every operation, every iteration of this loop uses what was just computed in the iteration before. So that's not going to work for parallel, not if you want to get the parallel time down. And to focus our mind, let's reduce the problem even further for a moment to just computing the sum of the array, right? So this algorithm does this in one particular order, and that's depicted in this tree. You have n inputs, n numbers that you want to sum up. And what we have is a binary addition operation that can take 2 numbers and compute its sum. So you inevitably have to do n-1 additions because it's a binary tree. There's no way to get by with fewer internal nodes. But what you can do is look at a different binary tree. That's the binary tree that belongs to this code. You always compute it, the previous sum, and then add 1 more element to it. You don't have to do this tree. You can do a balanced tree instead. And now, if you compute this bottom up, you notice that a lot of things, the way the tree is already drawn shows this. A lot of things can be done in parallel without data dependencies. I can add these 2, and I can add these 2. They don't interfere each other. So I can do level by level bottom up. This is the first time step. That's the second time step. And then there's one last time step. You see it gets less and less busy. So here 4 PEs were busy, here just 2, and then just 1. But we reduced the height of the tree. Here the height was, 7? And here it's just 3. Okay? Cool, so we want to do that. And the only bit that's left is to do this not just for the sum of all numbers, but all the prefix sums as well. And it turns out that you can do this with a simple a simple trick. You basically simulate this algorithm for all the prefixes all at the same time. And you can reuse some of the partial examples. So I'll show you how this works on an example, and then we'll have some code after that. Here's your input. In round 1, you take adjacent pairs and add them up. So this new cell is filled with these two and their sum. And you do this for all the entries. Note that the sums are overlapping and all that. We'll come to it. I want to point out that after this first round already, the first entry is final. Well, it was ready right from the beginning. And the second entry is final. It contains its prefix sum, but all the others aren't. In the next round, we'll do something similar, but this time we take the element that's above us and 2 steps back. And maybe you can just, by pattern matching, guess how this might continue. You double the distance you jump back in each step. So here we went back 1 cell, -1, I guess. Here we went back 2 cells, 4 cells, hard to draw, and 8 cells. Whatever the gray arrows are right, and whatever I'm drawing may or may not be. If you pick out any specific element, you can see the binary tree that we've had for just the sum embedded in this. There's maybe a bit thicker. So we have these two. And the trick is that the final sum consists of 2 subtrees, each of which consists of further 2 subtrees. And what we'll have to see is that eventually everything's covered. Sorry, I'm just blindly continuing here. It's not what I wanted. This one and this one. And these two. Now I will color in all the top row, won't I? Apart from the last one. Let's make that a bit more economically. Okay, I'm totally messing up the picture. But maybe you can see the binary tree a little nicer now, and I forgot one. No, sorry. That's the only one that shouldn't be in there. Yeah, that's subtle. It's not a complete binary tree. That's why I picked the second to last. There's one dangling leaf left here. What you can see just visually is that all the elements are in there. And it's the same binary tree that we've seen before. All right, but doing it this way, you get all the binary trees at the same time. Writing this in code is not too hard. It's just a little messy because you have to keep track of the indices. But that's what it looks like. We'll do the rounds. These are round 1 and so on. That's the height of the tree. The rounds go from 1 up to log n rounded up. Step is how much do I jump back for my single addition? That's powers of 2, as hopefully you've noticed that pattern here as a computer scientist. So that's the step size. And then the parallel part is just this inner loop. In each round, we do for each of the positions in the array. So in round 2, for each of the positions that are not final, that's why this starts not at 0, you compute first the new sum, the value that's above you and the one a little further to the left. You compute that sum and then you store it. Now, I might have written these 2 lines in 1 line, right? It's doing the same thing. Now, I split it up in this case to point out a subtlety here, which the PRAM model is essentially fine doing it that way, but you have to be careful if you implement this on real software or programming languages with parallel support. we have to make sure that all these reads in that line from all the processing elements are done before any of the processing elements start writing back their results. Because otherwise you would read the new value and they would get out of sync. You have to make sure that all the reads in round I are done before all the writes in round I, and then you can continue with the next round. Is it clear why? Otherwise, you might end up having some numbers summed more than once because one processing element ran ahead and already did a bunch of additions. Now you grab this and pretend it's the old value, but then you add things several times. So that's one of the things that are easy to write as a PRAM algorithm, but need explicit synchronization if you do this in most implementations. Synchronization is implicit for us, which makes the code clean. But I wanted to point this out here. OK. We still have to analyze how fast that is. Remember, we had sequential time linear. That's the goal for the work. Now, I know the answers are here, but let's go slowly over this. And I have two colors because we want both work and time. So let's first be in time mode, so the green one. We run the overall, the outer loop is not parallelized, so we have to do this sequentially. So we have log n times this inner loop. Now, this is one step, but that's constant. But then we have a for loop that's parallelized. So for the time, we can ignore this. We just look at how long each body takes. And that's, again, constant time. It's just two operations each, or a bunch of reads, an addition, and a write. So what does that mean for the overall loop? It's log n times constant. So we have log n overall. That's the time. OK? It will turn out that this is basically best possible for this problem, at least for some of the parallel models. If we look at work, the only difference, so this is the same. This is the same. The difference is that this loop now is done for all the different pre-E's. We sum that up. So we have to sum up this. And I'll be generous and say this is order n. Some iterations later are cheaper. But let's just do a generous upper bound, which turns out to be a sharp theta bound. So you have linear in each iteration, and overall n log n. OK? You could write this here more specifically by subtracting the step and then write it as a sum, and you'll come to the same overall theta conclusion. So we have n log n work, but a sequential algorithm that we've seen before was linear. So it's not quite work efficient yet. It's a bit worse. But hey, it's not that bad either, right? It's a log factor overhead. So unless you have really few processing elements, maybe that algorithm is still a substantial improvement, because the sequential time is really fast. It goes from linear to log. The best possible here comes in a way from just looking at the sum. If you look at the simpler problem of just summing up n numbers, as long as all you can do is take two numbers and add them up, you have to spend log n, you have to spend a linear number of additions. And you can work out that it's not possible to interleave them better. The binary tree has to have log n height. In a way, this is not atypical. We often have a certain trade-off. We can get a bit more parallelism, but then blow up the work. We've seen that as an extreme case for our first string matching algorithms. Now, sometimes, though, you can actually get the best of both worlds by just thinking a little harder. In this case, there's two ways how you can make our parallel prefix sums work efficient and keep the parallel time. You can do it with doubling the parallel time, which is a little more involved, so I'm not doing that. I'll show you something that effectively triples the parallel time, but brings the work down. So in theta world, where we ignore the constant factors, we keep the time but bring the work down to linear. Let's see how that works. And that's again, before we dive into the details, I know it's a wall of text. I should have split that up. The key thing is that this is a template that works more generally. If you have an algorithm that's good in terms of parallel time, but not work efficient, try to find a way to break the problem into blocks where you can use an efficient sequential algorithm on small pieces, and then on the aggregate results, use your work inefficient parallel algorithm. If you can reduce the size of the problem enough so that this work inefficiency doesn't carry through, and the blocks are small enough for the sequential algorithm to still be fast, you can improve overall. Again, as always, I'm not sure if it's useful to first give the general template and then the example, or the other way around. You usually understand things the other way around, but I think warning you up front about what's to come is helpful. You'll be my judge. Here's how we do it in this case. We choose a block size of roughly log n. So this will just be sub-segments of the array of log n elements. We break the conceptually break the element into blocks. No sawing needed. And then in parallel, we compute the prefix sums on just the little pieces. For that, we use the sequential algorithm, and then we'll use the sums of these in the work inefficient parallel prefix sum. And let me show you an example for that. At least like not a fully worked one, but a conceptual one. I think that makes it a bit clearer. So we start with 12 elements in our array. And suppose the block size is 4, which it is if you take the log of 12. I didn't just make that up. Good. So we'll have 3 blocks, right? If there are 4 elements each. I'm just trying to draw the array with cells. We don't really care about the numbers in there. That's why I said it's not a concrete work example. We're just summing numbers up. You can sum numbers. We don't need to do that in detail. So this is index 0, then 4, and then 8. Right, so let's look at the different steps. The first one is this local computation, where we keep local to the blocks. So we have conceptually broken the array into 3 pieces containing the same numbers. And you know what? Let's make it a concrete example, but a boring, trivial one. Let's just say it's filled with 1s. It's easy to keep track of the sum then. But it's a little less opaque. The local prefix sums, they just compute the prefix sums in this block using the sequential algorithm. So I will fill this all with 1, 2, 3, 4. Okay. Then the next step says take the last element of each block, namely these guys, the rightmost element, and compute the prefix sums for those using the new algorithm, the one with the fancy binary trees embedded. So we take this one, and this one, and well, I guess pretend there's a huge array with just the force in there, and compute the prefix sums of these. So that will give us, that's before, and then after you get this. Okay, that used up much of the slide's space. We'll see. And then we come back to the blocks. And add the global prefix before that block to all the values within the block. So what that's supposed to mean is we copy our orange part. Okay, I went too far with this one. Let's make this a bit smaller. This step says to all elements in here, add the 4. To all elements in this block, add the 8. I can do this in parallel over the blocks. So what I'll get is these stay the same. Then these get to 5, 6, 7, 8, and these get to 9, 10, 11, and 12. That's a 12. Okay, which is the correct prefix sum. Obvious to check in this case because we started with all ones. If you sum up as many ones as you have, then it should be the just the numbers 1 through 12. That was the last step. So that correctly computes the prefix sums. At least it worked in this example. Now let's see what the time and span for this and work for this is. So let me put time here and work there. Then I can keep using my colors for the different phases. How much time do I need inside each block with a sequential algorithm? Well, how long is a block? It's b long. So for the orange part, I need theta b time, which is log n. Then I have the blue part, which uses the fast parallel prefix sum algorithm that we've just discussed, and its time was log n. But I'm using it on n prime, which is not n, but n divided the block size. Rounded up, so in terms of theta, it's n divided b. And that, again, is n divided log n. So we can say this is still, should I do the computation? If you take, sorry, this is a log n prime. I didn't write this. That's the size of the input, but the time for the blue part is log n prime. If you insert this definition of n prime into log n prime, then you get log n minus log n. That's the same as theta log n. And finally, the green part, that's a bunch of additions. Again, each processing element deals with one block, so it's only linear in the size of the block again. So the overall time, if you sum this up, is something like 3 times the previous time. And, well, I don't have to copy this, so this is summarized here again. I think the explanation is better explained step by step. So the time is, in terms of theta, still the same, log n, as we had it before. Let's look at the work, because the work was where we weren't happy previously. So work for the orange part, we're using the efficient sequential algorithm, and it's effectively the same as the span in this time. Every little piece just executes on its block. So that's log n. In terms of the work, sorry, that's per block. And we have n over b blocks. So that's linear work overall. For the orange part, the local sums. For the blue part, we're using the work inefficient algorithm from before. So the work there was n prime times log n prime. If we insert what our n prime is, we see that this nicely cancels. So it's n divided log n times log n prime, which we've already seen is log n, minus this small term. So that cancels and becomes also theta of n. So we've reduced the work by making the problem a little smaller. We reduced it by a log factor. And that was enough to bring the work to linear. And then the green part is, as before, we use n over b blocks, and each block costs us b, so that's linear again. So the overall work is linear for all steps. And that's work efficient because we know that's the best sequential algorithm. Okay? So that's probably the most involved algorithm we'll discuss in this section. It's more involved because it builds on other things, right? It uses previous algorithms as a black box. The nice thing about this, though, is you get an overall much faster algorithm without thinking too hard. You're just putting pieces together in a clever way. And that's much of the beauty in algorithms and data structures. Almost all the time, you do just this. You take pieces and put them together in a more clever, slightly more creative way. And that gives you a better result at the end. The magic or the skill is to know good pieces to put together and to see how they fit, which is sometimes incredibly hard. Even with a lot of practice, you sometimes don't see it as someone else does. But practice does help a bit. I have one last ingredient for this building block section, and that's this problem, which again sounds maybe a bit esoteric at first, but this will literally be used in the sorting part then. Suppose we have an array of numbers. We'll always have arrays of numbers, but we have a second array that tells us some of the elements are not interesting. I'm only interested in the elements that have a 1. And the ones with a 0, I'd like to not have there. So I'd like to copy out only the elements that have a 1 above them. We call that compacting a subsequence from an array. So you have a subsequence is a selection of the indices, so it's not a contiguous part, but could be spread out as you want. But subsequence means we want to keep the order as they appear in the original array. Now again, doing this sequentially is very easy, right? You go left to right, you keep a pointer to the next cell that's free. If you see zeros, you skip it. If you see a 1, you copy it out and move one cell further. Easy peasy sequentially. How do you do this in parallel? It's not so clear at first because it seems that, say, this 4, where this goes in the output seems to depend on what happened before in the sequential algorithm. But if you think about it for a moment, this is really just reusing what we've just done. you can use prefix sums on this bit vector b to figure out where the elements should go. Precisely for this 4, say, if we check where it comes from, the position in the array is essentially the number of ones in b to the left of that point. So we would like to sum up the number of ones here. If we sum that up, that's 5. And 4 is the 5th element. So apart from the plus minus 1, because we start indices with 0, that's the answer. So you can put this into code by this little algorithm. You have this b given as an array. We copy that out because we need b and we need to mess with it. So we copy it into C and compute the parallel prefix sums there. We're using one of the lovely algorithms you've just learned. And then we can do the following in parallel. If our processing element has one of those positions assigned that has a 1, then it gets active, otherwise it sleeps. And what does it do? It copies its element, a of j, into wherever c of j says it should go, -1 for the off by 1, we start indices at 0. Okay? So the trick here is this we know how to do properly in parallel. And we can use that to pre-compute where the elements should go. And then we do the actual data movement in a second step, in a second phase. That way we have decoupled the computation, like the sequential algorithm would go through this step by step and have this data dependency. The place where the element goes depends on the past. We have decoupled this by first computing where everyone goes and then moving them there in just one step parallel across all the processing elements. So let's see if you digested that part. How fast can we do this compacting? It's also interesting that it doesn't depend on how many elements you copy out. It's kind of irrelevant for the time and work in this case. I'm a little pressed for time, so I'm probably have to cut it here and reveal the answers, even though maybe you didn't have a chance to vote. But most of you got this right, so maybe this is easy enough. The answer is log in time and linear work. And the reason for that is look at this algorithm and analyze it. It basically does the prefix sum and not much else around it. What comes afterwards in terms of time is a constant step. And linear work, because we spread it across all the PEs. But both is dominated by the computation of the parallel prefix sums.